Now we're going to look at a slightly more ambitious example. Let's consider a system which comprises a number of resources, some of which are in a live state and some of which in an idle state. You might think about something like an operating system with a number of processes, some of which are operating and some of which are in an idle state. But a given resource, a given process, can't be both live and idle at the same time. So here's our system description, call it system. There are two observations, live and idle, and both of these have this type here, power set of resource. What does that mean? Well, if they have that type, that means that live is a set of resources and idle is another set of resources. So we're talking about observations which correspond to sets of resources. Live, obviously, corresponding to the set of live resources, and idle to the set of idle resources. And the constraint that we talked about just a moment ago is here, and that's to say if you take the two sets, live and idle, and you take their intersection, then you get the empty set. There's nothing that's both in live and idle at the same time. Okay, so that's our system description, that's our schema, and that clearly induces some rules. But what are those rules? Well, we have the various rules for schema sets and for propositional logic. So we can use these to simplify, and we obtain the following rules as our theory for the system. Now I shan't go through those here, but we can work through those in class. So here is our first introduction rule. In fact, it's the only introduction rule. And that tells us that a state is in the system if the live set and the idle set are disjoint. That's to say, if a resource Z is in the live set and a resource Z is also in the idle set, this leads to a contradiction. What do we have in the case of the elimination rule? Well, if we know that something is a system, if we know that S is a system, a reasonable state of the system, then if R is a resource in the live set and R is also a resource in the idle set, then this is a contradiction. So there's our little theory. The only thing we've got to be a little bit careful about in that theory is that there is a universal quantification introduction implicated here, so these Z's here must be fresh. Obvious operations on this system might be to force awake or to make dormant a given resource. How would we do that? Well, here's an example of an operation. We call this operation here wake, and the declarations are as follows. First of all, we have delta system, which as usual is shorthand for system and system prime. That's to say there is a state space system which describes the before state, and there is a system prime describing the after state. And in this particular case, the wake, we're going to have an input R query, which is a resource, and that is the resource that we're going to force to be awake. What are the constraints in this? Well, first of all, we can't wake something that's not idle. So we want our query to be an element of the idle set in the initial state. Now, what's the final live set? Well, it ought to be what it was before, together with the resource that we have just woken up. And what is the idle set afterwards? Well, it should be what the idle set was before, with the resource that we've woken up removed from it. We also might like an operation to put a resource to sleep. So here we have it. Here was our operation schema called sleep. Once again, the declaration involves a change in the system and system prime, and it involves an input R query, which is a resource. The constraint is rather similar to wake. In this case, though, of course, we want the resource to be currently live. That is, in the initial state, it had better be in the live set, otherwise we can't put it to sleep. And then the live set afterwards will be the same as the live set before, except the resource will have been removed, and the idle set afterwards will be the idle set before with the resource added. Well, if we specialize the general introduction rule for schemas, in the case of the operation wake, this is the introduction rule. So, as a conclusion, of course, we have what it means for a state transition to be in wake, that is S0, the before state, S1 prime, the after state. So a pair S0, S1 prime is in wake under certain conditions. These are the conditions. That S0 is a system, a legitimate state of the system. S1 is also a legitimate state of the system. And now some other conditions. First of all, the input resource, our query in the initial state, is in the idle set in the initial state. The live set in the final state, the after state, is the same as the live set in the initial state with the resource added. The idle set in the final state is the idle set in the initial state with the resource in the initial state removed. And under those conditions, that state transition belongs. Now, I'd like to just say a few words about why these first two premises of our rule are present. And the reason is that being a state of the system is not trivial. It's not just simply a matter of obeying some typing conditions. There are some conditions that you have to be a proper system. So we do need those premises in this particular case. The other thing that I want to note is that S1 prime is the after state. S1 is that state treated in the unprimed sense. There is little point in writing S1 prime live prime here, although that would be equally correct, so we just remove them. That's because it's possible to go between a state, the prime version, and back again to the original state by priming once again. Now, you will have seen that there are 5 premises in the introduction rule for the system operation wake. So there are 5 elimination rules here, and they're fairly straightforward. First of all, this one. If you've got a state transition in wake, then the before part is legitimate system. Similarly, here, if you have a state transition in wake, then the after state is a legitimate system. And once again here, you notice the primes are missing. Could quite easily have written S1 prime element of system prime as a conclusion, but there's really no point. The third elimination rule, if you have a state transition in wake, then the resource in the initial state is idle in the initial state. The fourth elimination rule, if you have a state transition in wait, then the live set in the final state is the live set in the initial state with the resource added. And last but not least, if you have a state transition in wait, then the idle set in the final state is the idle set in the initial state with that resource removed. Now, there is a proposition in here, in this particular operation, the syntactic precondition, which simply says that the resource has to be idle. Okay, now that's conjunctive in the specification. In other words, we read all the constraints listed in a Z specification as conjoined, as joined with and. So I'd like you to consider a before state S0 in which the resource R prime, the input we give it, binds to a resource which is not in the idle set. So it fails to satisfy the condition that R in the initial state is in the idle set in the initial state. So that means there is no state S1 at all such that S0 star S1 prime is in wait. So the specification is a partial relation. There is no legitimate output for some initial configurations. So bindings outside the precondition are not associated with any after states whatsoever. Now, suppose we wish to mark the success of waking up a resource. And we might do that with the following operation. Wake success. It has a single observation, message shriek. There's an output, which is a string, and we simply say that that message shriek should be wake succeeds. And the theory there is extremely straightforward. Here is the introduction rule. A state in wake success is a state in which the message shriek has the value wake succeeds. That is both the necessary and the sufficient condition for being a state in wake success. And then we could combine that wake success with wake to form a new operation, which we'll call wakes, which marks that success. That is, we use this as a definition of wakes. It's what we had before as wake and wake success together. Well, the interesting question is, how do we know it's right? How do we know that conjoining those gives us what we want? What do we mean by right here? Well, presumably we mean captures our informal ideas about what the wakes operation should do. In Z, generally, one typically reduces the composite expression, the conjunction, to a single atomic schema and then just looks at it. And that requires us to rely on the equational logic of Z, which we looked at before. In other words, we use the equation here, this one here, this equation here, which we've seen before, to reduce the conjunction, which is on the left-hand side of this equation, to a single schema, which we looked at earlier. Well, if we use that equation on our example, we could simplify wakes to this single atomic schema that appears on this slide. And we could look at that and inspect it and say, well, yes, that gives us some confidence that the definition we made of wakes to be the conjunction of wake and wake succeeds is indeed what we wanted. But is it really the right thing to do? The whole idea of Z, and one of the most powerful things about it as a specification language, is that it gives us a way of structuring specifications, of building large complex specifications from smaller ones in a modular fashion using connectives. Surely the last thing we want to do in order to be clear that we've actually specified something in the right way when we've put them all together using these various connectives is to reduce the whole thing to some enormous, potentially enormous atomic schema and then inspecting it. It runs completely counter. Because we're treating the language in the logical way that we are with introduction and elimination rules, rather than using the equational logic to reduce complex expressions to single atomic schemas, we can simply look at the introduction and elimination rules for the schemas that we define in a modular way. And that is what is going to give us confidence, and particularly the use of those rules in proving properties is going to give us confidence that we've made the right definition. Well, what are the introduction and elimination rules? Well, here's the introduction rule. It tells us all the conditions which are sufficient for a state transition to be in wakes. Just looking at that gives us a lot of confidence that the definition of wakes is correct. And here are the 1, 2, 3, 4, 5, 6 elimination rules for wakes, which also give us a lot of confidence that we've got the right definition for wakes. Moreover, any properties that we prove using these introduction and elimination rules will give us additional confidence that we have made the right definition. Much better than trying to reduce the complex modular specification to a single atomic schema and just looking at it